A presentation on Lab 2. Um, the purpose of the lab is to use a magnet to create a system where we can show the properties of Biot-Savart's law to measure a magnetic field, and we also create a computational model of our system to simulate the experiment. Um, some of the equations we're going to use from the lab PDF. The top one is going to come in handy when we have a regression based on our data points, and we need to find the um, given k and n values to calculate our field for the bar, which we will do in the second equation. And the last equation is going to be important when we deal with off-axis calculations um, from the magnet. The procedure, there's 5 main parts to the procedure. First, we want to download a magnetometer app where we can measure components of the magnetic field. We have to align the magnetometer to the Earth's magnetic pole so we don't get skewed data. I'll explain that later. We also need a meter stick to measure our distances, and we keep our phone, or I kept my phone perpendicular to the meter stick and try to maximize the x distance to make it accurate with the given distances from the Excel sheet. And we then measure the different magnetic fields using the magnetometer at various distances. And finally, in our last part, we're going to compare the field along a 45-degree axis with a computational model. So from our Excel file, we fill in data based on the distances and the different magnetic field values for a magnetometer, and we get this equation that is a representation of the first equation I was talking about earlier. Using so our n is simply the slope of the line, which is negative 2.2, and our k, we computed this value using ln properties. Essentially, we just raised the y-intercept, we raised e to the y-intercept power. And finally, using that equation, we calculate our mu to be 4.48. So in our computational model, I didn't really bother creating all the graphs or all the vectors for every single observation point, because we mainly were considered with the off-axis point. And the computational model gave us a magnitude for the 45-degree offset off-axis to be 3.86 times 10 to the negative 5. And our experimental model, as you can see here, gave us 6.36 times 10 to the negative 5. What I noticed with the general values is that when calculating with the magnetometer, that when the magnetometer is far away from the magnet, the magnetic field calculation tends to decrease a lot, and as it moves closer to the magnet, the x component of the magnetic field increases. In regards to the what if questions, like I said, if we had not oriented our setup so our magnetometer wasn't aligned with the magnetic North Pole, then the results would have been skewed because the constant vector of the magnetic field due to the Earth's magnetic field would have been accounted for, and this would have made the calculation of the magnetic field off axis to begin with. So if we had two connected magnets, the magnetic field would be stronger because the magnetic moment would increase, but the distance would probably remain the same because or or I should say the rate as which the magnetic field decreases in terms of distance would stay the same because this is a property of a dipole field, and not the magnet's strength. So it's based on the actual charges of the two connected magnets, which are identical, so it stays the same. And some possible sources of error is that, as mentioned in the lab report, we had to minimize the other electrical devices, but there could be some noise with that still.